Hey everyone. So in this video, we're kind of going over something that's been a sore subject for a lot of students because it's something that a lot of students are struggling with. So this past month, we've really been doing a deep dive into the skill of factoring. We've been factoring polynomials, but more specifically, we've been focusing on quadratic trinomials, right? And so let's say that we have a general form, ax squared plus bx plus c. Now, we saw a couple different examples of how this quadratic trinomial could look, right? So we've seen the case where a equals 1, so something like x squared minus 8x minus 20. And then you guys know to use your BCPQ method, where, right, uh, oops, you have c at the top, b at the bottom, you're multiplying to c, you're adding up to b, and so you're finding factor pairs of your c term that add up to your b term, -8. Okay, and then eventually for this example, right, you would get something like -10 plus 2. Well, -10 times +2, that multiplies to give you -20. -10 plus 2, that adds up to -8. There you go. You found your p and q values such that you can factor this quadratic trinomial in the form x plus p times x plus q, right? So you can factor like x minus 10 times x plus 2 because these represent your p and q values. Now, that's not really the issue because the thing is that I think actually most of my students are very good at BCPQ method. Now, the real problematic things start happening once we get into our quadratic trinomial ax squared plus bx plus c, where a is not equal to 1, right? And so let's look at an example. So something like 15x squared plus 14x minus 8. Okay, well in this case, our a is equal to 15. And if you try to apply your regular BCPQ method, right, where you're trying to figure out what can multiply to your C and add up to your B, right, it's not going to factor out to be correct, right? And so a method that we've been using with these manipulatives, like these tiles that are purple and green, is this method of guess and check. And when we were learning how to do this method, we realized, okay, you're not really guessing and checking because there's some number sense going on where you're trying to guess and check the factor pairs of -8 and 15 in such a way that when you multiply those factor pairs together and add them together, right, then you end up getting 14. Okay, well, sometimes this can take a very long time, right? And you could easily mess up by doing the guess and check method by just simply forgetting about a pair or a combination of factors. Or let's say that you did a factor pair and you thought that you checked the switched version of this and it didn't work out, right? There are plenty of ways that this can go wrong because this is a very cumbersome and time-consuming method. So someone told me about this specific method that's a surefire way of always factoring quadratic trinomials correctly where your a is not equal to 1. The first person that I saw do this was my coworker Nancy, but then when I looked into this further, right, I found this method kind of seems to originate from a YouTuber named NancyPi, and she makes a lot of really good videos just kind of explaining how to do something. But then what really made me kind of step back was think about, okay, well, the algorithm that NancyPi has works really well, but how does it really work, right? Why does it work, and why can we use it? Because it's kind of not super useful to just know how to use an algorithm or to know how to do a procedure without understanding why you can use it, right? Because then it just becomes a list of steps that you memorize, which you can also very easily forget, right? So I think if we know why this works, then using it in the future is going to be much more useful. So that's just like some context, right? Why don't we actually go into this method from NancyPi in order to factor this quadratic trinomial here. And then let's go into a proof to kind of see where this is coming from and why this works. Okay, so we have this quadratic trinomial over here, and we're going to be using NancyPi's method of using something called a magic x, right? Now, you don't have to actually use this diagram in order to help you, right? You can also just think about it and kind of just do the procedure over and over again, but it's essentially the same amount of steps. Okay. So right now I have a quadratic trinomial where my a is not equal to 1, right? My a is 15. So what I'm going to do is I'm going to just get rid of this 15, and I'm going to turn this into x squared plus 14x, and I'm going to change my c term such that I'm multiplying it with my original a term. So this gets multiplied over here. I get minus 120. Okay, so all I did was drop my a term and actually just multiply it with my c term. Okay, so I did that, and now this becomes a BCPQ problem, right? So I just need to figure out what are two numbers that multiply to negative 120 and add up to positive 14. Well, I know that I'm multiplying to a negative, so my sign combination has to be negative and positive, right? And then if I think about my factor pairs of negative 120, add up to 14, right? Then I end up getting 20 and 6. Oh, other way around. There we go, right? So 20 times negative 6 is negative 120, and then 20 plus negative 6 is negative 14. Oh, sorry, positive 14. So we know that we factored this correctly. We found our P and Q. So if we were just using our BCPQ method, right, the way that we would factor this is we have these two binomials. We have x over here, and then I'm going to add 20 and subtract 6. Okay. Well, we know that this is not an equivalent form to our original expression, right? This is an equivalent form to our transformed expression when we dropped that a term and multiplied it with our c term, right? But that's not really an equivalent expression that we are trying to factor to, right? And so we need to do an extra step. So because we multiplied our c term with 15, we need to divide our c term by 15. Okay, and so when I do this, I can actually simplify each of these fractions. So I have 20 over 15. This gives me 4 over 3. And then this gives me negative 2 over 5. Okay. Well, this bottom term represents the coefficient of my x term in this binomial. And this term, my numerator, shows me what I'm adding to my x term in my binomial, right? So the way that I would factor this would be 3x plus 4 and 5x minus 2. Okay? So if you actually multiply this expression out, you see that it's going to give us our original expression of 15x squared plus 14x minus 8. Now, depending on who you are and what you like, right, this might be more complicated or more confusing, but it works, and it's going to work pretty much every time. So why don't we go into why this actually works? Because what's going on here is seemingly magic. Like, why are we dividing by 15 here but not over here? How are we getting an equivalent expression when we do something that's technically illegal in math? Okay, so let's go over a proof of how this actually works. Okay, so now that we know how the NancyPi method really works, let's actually go ahead and try to figure out why it works and why we can use it. And it's not magic that's coming out of it, but it is a really interesting relationship or equivalency that NancyPi discovered, at least I'm assuming that she discovered, which allows us to kind of use this method in order to factor trinomials. Okay, so this hinges on a couple things. All right, so let's say that I have my quadratic trinomial ax squared plus bx plus c. Okay, and I'm saying that I can reduce it down to this form, rx plus p times sx plus q. Okay, and then I'm also assuming that all of these values, so a, b, c, r, p, s, q, right? These are all not 0. These are all integers, right? So that when I factor this, it actually works out, and also they're not 0, so that when I actually am dividing by one of these variables, I can actually divide it out without having to worry about dividing by 0 possibly. Okay. Well, in NancyPi's method, right, what we actually do is x squared plus bx, so we just drop that leading coefficient of a, and we multiply it with c. So our final term becomes ac. And she claims that this is reducible to this form x plus h times x plus k, right? And there are a few relationships that hold, but before we go into those relationships, I also want to just state that h and k are also same value types as our B, our A, and C, our P, S, and Q, and the fact that they are not 0 and they are integer values. And so when we think back to the claim of NancyPi, right, in this method, what she's really doing at the very end, where this magic starts happening, is she's taking these H and K values, right? She does H, well, it's not an H, it's an N. She does H divided by A, and then it reduces down to some simplified fraction, right, some simplified form, such that we produce our P value and our R value in our first binomial. Similarly, right, if she reduces K with A to its simplest form, she claims that we can actually end up getting our Q and S values in their simplest form, right? And so this is a relationship that she has noticed, right? She's not making an equivalency, but because of this relationship, right, this is how we're able to very easily factor these trinomials. Okay, so let's actually see how we can get these ratios, because if we can find these ratios and create this proportion, right, then we know that we can actually use NancyPi's method. This is kind of like unlocking the why, or how this is actually happening in her method. Okay, so let's actually start expanding things, start making some equivalencies, so we can eventually get to this point. So if I expand this out, right, I'm expanding Rx plus P times Sx plus Q. I have this. I have ax squared plus bx plus c is equal to Rs x squared. Okay, plus let's do PS plus RQ x plus PQ. Okay, so we can start creating some equivalencies, right, where A is equal to Rs, B is equal to the sum PS plus RQ, okay, and then C is equal to PQ. All right, now let's do the same kind of deal with x squared plus bx plus ac, right? So we know that this expands to x squared plus h plus k x plus hk, right? And this relationship between h and k is very similar to, if you think back to like BCPQ, right? H times k will equal AC, or a constant term. H plus k will equal our middle term. Okay, well, let's set these equivalencies just like how we did for the previous equation. So we have that this time B is equal to H plus k, and AC is equal to HK. Okay, well, now this becomes a transitive property of equality problem. So let's actually substitute in these values. So we have PS plus RQ, and we have Rs, so that's A times C, which is PQ. Okay, now I want us just to remember that what we set as H and what we set equal to K is completely arbitrary as long as these relationships still hold. For the purpose of this proof, I'm going to set H is equal to PS and K is equal to RQ. And if I actually multiply these together, then I get RSPQ. If I actually add these together, I have the exact same sum that I had before. Okay. So now that I've created these equivalencies, where H is equal to PS and K is equal to RQ, let's actually go ahead and see if we can set up this proportion. So we have H over A, right? And so H is equal to PS, A is equal to RS, because S is not 0, right? I can actually divide this out, and I have P over R, right? So this is our simplest form of that H term, right? And so I end up getting P over R, and then I have K over A is equal to Q over, RQ divided by RS. Those R's can cancel out because, once again, they're not equal to 0, and so I have Q over S. Okay, and so NancyPi's form said that we have x plus p over r, x plus q over s. right? Now, she is not saying that this is equivalent to this. We know that that is patently false because h is not the same as h over a. However, she does notice that when you take h and divide it by a, right, its simplest form is going to result in your terms p and r. Your simplest form for k over a is going to result in your terms q over s. And so because we have these cool number relationships going on, right, it allows us to really easily kind of break down this problem, right, because we have every element that we would need in order to factor out ax squared plus bx plus c into its reducible form. So kind of satisfying, kind of not satisfying, right? That just like, it was really just a number relationship that she discovered, right? But it's a number relationship that works. So if you find this method to be easier for you, then go ahead and use it over and over again because it's pretty useful. But if you don't understand how this method works, I would really highly recommend against using it because I think when you use this, you end up getting kind of wrong ideas about equivalence when we actually factor trinomials. Okay, so hopefully this was useful. Hopefully this answered some questions. But yeah, if you'd like to go over the proof again, just bring it up in person and we can go over it in person.